My name is Ling Zhu. I'm an assistant professor of sociology and also the co-director of CSSL at UHK. I will be the moderator of today's talk provided by Professor Xu Yiqing. Today, we are very happy to have Professor Yiqing Xu from Stanford University to be here and share with us his recent research in the area of causal inferences. Before I turn the table to Professor Xu, please allow me to spend several minutes to introduce him to you. Professor Xu is an assistant professor in the Department of Political Science at Stanford University, and he is also affiliated with Stanford Causal Inference Center and the Stanford Center on China's Economy and Institutions. And Professor Xu is well known for combining methodological insights with substantive topics. His primary research area as a methodologist are about causal inference techniques, and as a political scientist about comparative politics. And in recent years, his work has focused on mainly developing and applying causal inference techniques and methods for panel data. Professor Xu, as many of you may know, is highly prolific. His work has appeared in many top-tier journals in political science, such as AJPS, APSR, and Political Analysis. He has received multiple awards from the Society for Political Methodology to acknowledge his contribution to this field, including the Best Dissertation Award, the Political Analysis Best Paper Award, the Political Analysis Editor's Choices, and the Best Statistical Software Award. And in 2024, he was further named as the Society's Emerging Scholar, which is a great honor to recognize his exceptional contribution to the field. Today, we are very happy to have him sharing with us his recent study on factorial difference-in-difference, which is currently under minor revision in JSA. Without further ado, I will now turn the table to Professor Xu. Let's welcome.
Thank you, Juling. Can you hear me? Okay. Okay, great. I'll get started. Thank you for the very kind introduction and for the invitation for sharing our work at CSSL at CHK. I have been a long-time follower for your platform, and I think it's doing a lot of good, great service for the community, especially building a bridge between academia in different places of the world. Today I'm going to talk about a collaborative work with Anqi Zhao from Duke and Peng Ding from Berkeley. Both are great statisticians. And we frame this as a factorial difference-in-differences. You will see why we choose that name. I'm sorry, I apologize first that we're kind of introducing another twist to the DID literature, which is already very vast growing very, very fast in the recent years. Okay, so motivation here. This is actually motivated by a research of myself in 2022 when I was working on this applied paper with two economists. We're interested in whether social capital have any impact on famine relief during China's Great Famine. All right, so the data structure is a panel data. It looks like this. And actually many applications in the social sciences look like having a similar structure. So to simplify the setting, we have a variable social capital that is binary, although in the paper we also have a continuous measure of social capital. It is measured by the number of genealogy, per capita level genealogy or 族谱 at a county level. And then we also have a county year panel of mortality rate. So we have a baseline factor we call G, which is social capital here. It is measured before the event. It is measured before the happening of the Great Famine in the late 1950. And then we also have an event, which is a famine that affects all the counties, affect everywhere in the country because it's a national policy. But in the panel data, we have before famine years, we have a famine years, and we have a post-famine years. All right, so this is the plotting of the raw data by level of social capital. Imagine this variable is a binary variable. So these two lines depict the average level of mortality rate across these two different types of counties. All right, you see very obviously that during the famine years, places with high social capital, the increase in mortality rate is smaller than the increase in mortality rate in places with lower level of social capital, which is depicted in blue, right? But obviously, both type of places are affected by the famine. As you can see, the mortality rate shot up from like 1% to almost 3%. Is very, very high during the famine years. But for those who have no idea, don't know the historical background, this is the most deadly famine in recorded human history. Like, tens of millions of people have died because of the famine. Okay, so in terms of the estimation strategy, that's the basic data structure. We also have covariates, but for simplicity, we don't talk about covariates right now. We are using a two-way fixed model, and here it's numerically equivalent to a difference-in-differences estimator because the timing of the event is the same for all counties. So there's no like stack adoption, no Goodman-Bacon type of criticism, right? So the idea two-way fixed are numerically equivalent. So here on this plot, as you can see, we plotted the so-called dynamics, the coefficient from the dynamics specification. These are the coefficients of the interaction terms between this baseline factor G, which is social capital, and a time dummy, a set of time dummies. So we chose 1957, 1 year before the starting of the famine, as the reference year, right? This is also very common practice. And this plot shows the evolution of the differences between high social capital counties and low social capital counties. So the question is, how do we interpret these set of estimates, right, from DID? So descriptively, in the paper we wrote, the rise of mortality rate during the famine years is significantly smaller in counties with high social capital than in counties with low social capital. These are just describing the difference in the coefficients, right? It's not, we're not using causal language, but we also in this paper include causal language, which we say we interpret these differences as the effects of social capital on famine relief. It's kind of a causal moderation. We think social capital is causally leading to a smaller impact of the famine on mortality rate. So that's our interpretation. And many papers using a similar structure use causal language because a lot of the social science papers do want to establish causal linkages, right? Okay, so this is not, as I said, this is very common. It's not rare usage of two-way fixed or DID estimator. It's actually very common in the social sciences, in economics, in political science, in finance. We have documented many examples of using the same estimator applied to similar data structure. Here we chose 4 examples from political science and economics from APSR, QJE, AER. They all share a similar structure. They all are estimating using an interaction specification with two-way fixed effects. So here, this paper by my colleague at Stanford, she's looking at the interaction coefficients of discrimination against German immigrants and World War I. So her argument is that the innate discrimination against German immigrants was amplified the impact of World War I. And then the outcome variable is assimilation behavior. It basically places with more discrimination with German immigrants when World War I happened. These German immigrant families Americanized the names of their children. And we have similar papers, like this is a QJE paper looking at how religion moderates the impact of the Second Industrial Revolution in France. Another paper by friends of mine, Joy Chen, Eric Wang, and Zhang Xiaoming, they look at in Beiwei, China, in Imperial China, elite strongholds, places where there are local elites, military powers. When the state trying to consolidate power, they recruit elites from these places, awarding them with official titles. And the last one is very similar to our setting, where we'll have a good friend of mine looking at in Russian famine in places with more Muslim share in the population, they suffer more in terms of mortality during the Russian famine. Okay, so the question here is, what are we doing, right? What are we estimating? We're using the same estimator, definitely, the same difference in difference estimator, but it seems to be different from the canonical difference in difference research design, right? Because in the Karl-Kruger DID research design, there's always a clean, so-called clean control group that are not exposed to the event, like Pennsylvania versus New Jersey. New Jersey was not subjected to the minimum wage increase as in Pennsylvania. Right. I'm sorry, the New Jersey was subject to, Pennsylvania was not subject to. All right. So we call this the research design factorial difference-in-differences because we try to bridge two literature. One literature is from the statistics literature on the factorial design. In the experiments, you may have two or more factors. Each of them are randomized. And this type of experiment has been analyzed by many famous people and is a classic in statistics. Another strand of literature, of course, is difference in differences literature, mainly from econ, right? So it was popularized by economists and awarded Nobel Prize in 2021. But here we're using the DID estimator, but it's slightly different from the canonical DID design that Karl-Kruger have popularized. Okay, so what are we doing with this paper? It's mainly a conceptual paper. The estimator is pretty much the same. We generate some insights on how to do estimation better, but I would say this is mainly about conceptualizing this particular research design, which we call factorial DID. So what is the research design? So research design, the way we use it is basically identification strategy. It is a combination of research setting, how your data look like, are you using panel data, repeated cross-section, and so on and so forth. And what is your estimate? What is the target parameter? Is this target parameter a causal parameter? What is your estimator, right? You can use different estimators to gain consistent estimates of an estimand. But what particular estimator are you interested in? In this case, the ID estimator. What are the ID assumptions and what are the ID results? Normally, we call this identification strategy, or some people also call it research design. This is slightly different from the usage of design in the statistics literature, because in the stats literature, especially in causal inference, when we say design, it's more about detailed information or exact information on how treatment is assigned or the propensity score, right? In experiments, of course, we know the design, but in other settings, we may or may not know the design very, very well. But here we use design or research design simply to refer to identification strategy, which is a combination of these items. Okay, so what is this about? In canonical DID, we have two groups, G equals 0, G equals to 1. What's very nice about this canonical DID design is that G, the group indicator, also determines exposure level, determines whether this group is exposed or affected by the event, right? In the canonical DID, G equals to 1 group is exposed and G equals to 0 group are not exposed. Of course, these are just labels. You can flip them. And then by the parallel trend assumption, no anticipation assumption, the DID estimator can identify the ATT for group G equals to 1, right? The average treatment effect on the treated for group equals to 1. So this is a canonical DID. But in factorial DID, a very interesting thing happened, which is, as in our case, all both groups or all units in the sample are exposed to the event. You cannot believably argue that one of the groups are not exposed. Obviously, famine affects the national policy. It's induced by a national policy greatly forward affect almost every county in the sample, right? And then we apply a difference in difference estimator. What are we doing? A simple answer would be we're identifying the treatment effect heterogeneity. This is not a controversial argument, and I'm sure a lot of people think that way, and a lot of others writing that way. And this is not necessarily causal, right? And imagine the parallel trend assumption still applies, and still is valid, and also no anticipation is also valid. The DID estimator is simply a difference between these two, this distance and this distance, which is and which is the difference between the two distances, which is how different the treatment effect of the event on the two groups of units in an associative, in a descriptive way. This is a right interpretation, but it's not a very precise interpretation, as you will see later, because we need to specify the potential outcome first. All right, this is not causal. We need additional analytical tools to clarify what we are doing, even we know this is associative. And also, when you have covariates, common two effects for models may need some augmentation, may need some modification to make them slightly more flexible. All right, so another contribution of the paper, of our paper, is that if we want to estimate G's causal effect, like if we want to say social capital has a causal impact on the effect of famine, then we need stronger assumptions. The parallel trend assumption and no anticipation assumption is no longer sufficient to identify G's causal effect. I want to say that in the paper that we review, when others suggest there's a causal effect of G, they usually understand that these canonical assumptions are not sufficient. So they try to argue a bit more, but I would say it's not entirely clear to them what assumption is a good set of assumptions or sufficient conditions for this to be true, to identify G's causal effect. And we want to clarify that point. All right, so we also show that when you clearly specify what is a factorial DID design, research design, we can also incorporate canonical DID as a special case with additional exclusion restriction, as you will see in the talk. Okay, for the sake of time, I will skip the literature review, but I just want to say this is obviously connected to the DID2 effects based literature. This is connected to the factorial design literature. This also is connected to the very popular, starting to be more and more popular Bartik instrument shift share research designs. Although what's different is that we don't have a clear measure of the treatment as in the Bartik designs. This also is connected to the Lord paradox, which is a classic paradox in statistical literature. The takeaway, Ruben has a very nice paper analyzing Lord paradox. The key point is that the paradox exists because the non-treated potential outcome is not very well specified, or people are using different ways to specify the specification for Y0 or the augmented Y0. And that is exactly what's happening here. Okay, so the rest of the talk, I want to first set up the problem and talk about defined estimands. There are a couple of different estimands that this setting can get at, but require different assumptions to identify. Then we talk about the identification results, but the identification results will only be graphical. I will not use much mathematics, but once you understand the graphics, I think the proof is fairly straightforward. And then we're going to talk about extensions very briefly because of time. The main extension is to extending to include covariates. and extending to continuous G. The baseline social capital measure, for example, is continuous instead of binary. And then we come back to our running example, which is the relationship between clan and famine and the mortality rate. Okay, but as I said, the key of this paper is conceptual, the estimands and identification in the simplest 2x2 cases. The simplest 2x2 case is the most important result for this paper. Okay, the setup, for simplicity, we focus on two group, two periods, no covariates. So here we draw these two cells, right? Because we have two group, two periods. And the timing is fixed. So you can think of the data as a so-called wide form data. We have a G indicator, we have Y pre, Y post. These are observed. And because it's wide form, if you want to draw inference, you don't need to cluster, right? Because it's already wide form. You can just either do robust and error or non-parametrically bootstrap based on the rows, right? Each row represents one county. Of course, when you have multiple periods, the matrix needs to be wider. Okay, so we have two periods, but we also invent one variable, quote unquote. It's quote unquote because it actually doesn't vary. The variable doesn't vary. It's just an indicator. We call it Z. Z is useful only for analytical purposes. It's a bridge we use to connect the factorial design with DID, all right? And because Z equals to 1 for all the units in the data, so it's not a variable, it doesn't vary, but you can imagine we just add one column in the data set, but it has no variation. It's important because it's connected to the potential outcome and it measures the exposure level to the event. Here Z equals to 1 for everybody because every county is exposed to the famine starting 1958. Okay, but compare this with canonical DID. You can think of Z equals to 1 for G equals to 1, Z equals 0 for G equals 0. This variable is redundant in canonical DID because it's the same as the variable G, right? Determined by the variable G. But what complicate things exactly is that the G does not, in the factorial DID design, does not inform the value of Z because Z equals to 1 for everybody. Okay, in terms of estimator, we're still using the difference-in-differences estimator. So I always tell my students that when you talk about DID, the second D is plural because it's a description, it's a literal description of the estimator. It's taking two differences, which is plural, and then take another difference of the two differences. That's why it's called difference-in-differences. It's a literal description of the estimator. So we are working with 4 averages, and then we take a difference before and after for one group, before and after for another group. Then we take another difference between the two groups. Of course, you can do it the other way around. It will be the same. All right. So in this talk, maybe with very like a 1 minute of digression as exception. In this talk, we mainly focus on this very simple DID estimator. This is just an algorithm. And this algorithm, under normal regularity conditions, will converge to tau DID, which is the probability limit, right? If n goes to infinity. And then we basically are going to talk about what this tau DID actually means, right, under different identification assumptions. So this is not an estimation paper, it's an identification or conceptual paper on how can we interpret DID correctly under different identification assumptions. And this obviously is the population expectation of 2 before and after difference on observed Y between groups G equals to 1 and group G equals to 0. Okay, so Now we have the estimator. We know what to do with estimation. Now we're going to talk about the our target parameters, right? Some of them are causal, some of them are not causal. So we frame factorial DID, this research design, as a factorial design with two factors. Just like in a normal, in a commonly see factorial experimental design, you will, because you manipulate two factors or two treatments, you have two factors, right? Here we frame it as having two factors, G and Z. We use a small non-capitalized G and Z to indicate that their potential outcome in the indices. They're not observed values. All right, so potential outcomes are augmented with two indices, and you also have the t dimension before and after. So you basically have 8 potential outcomes. Here, this is for the same unit, because you have 2 periods, you will have 8 potential outcomes. So when g equals to 1, z equals to 1, and in the before and after, you will have 2 potential outcomes, okay? What are the observed outcomes? The observed outcomes are those we don't need to estimate, we don't need to rely on assumptions. We can only rely by connecting observed outcome with potential outcome, we can directly observe them. So this equation is a conventional consistency requirement in the causal inference literature, which connects observed outcome with potential outcome. Here, the black ones, but that black potential outcome can actually be observed, but the red ones, the 4 red potential outcomes cannot be observed, but we still need them for certain causal estimands. And because we need them, we need to use identification assumptions to basically either eliminate them or connect them with observed outcomes, right? So why the red ones are not observed and why the black ones are observed? Because for g equals to 1, for big G equals to 1, first of all, everybody is exposed, right? So big Z equals to 1. So we only observe Z equals to 1. That's why the black ones are observed. But for G equals to 1, we observe the top. For G equals 0, we observe the bottom 2. The red ones, because the second index is Z, we never observe Z equals to 1 in the data set, even the before period, because these are the cross-sectional, right? These are not changing over time. These 4 red ones we never observe, okay? So what are the causal quantity of interest? So first we start with, these are not identified, but we start with individual effects. The first individual conditional effect is when we fix G, and we look at given G equals to small value, small uncapitalized G, what's the effect of Z, right? That's the conditional effect of Z conditional on G. And we can symmetrically also define the conditional effect of G conditional on Z, right? And then an interesting quantity in the factorial experimental design literature is the individual interaction effect, which is a difference in differences of the 4 potential outcomes, right? Y11 minus Y10 minus Y01 minus Y00. Again, these 4 potential outcomes are the potential outcomes of the same person, of the same unit. That's why it is causal. So when by convention, when you're comparing potential outcome of the same person, same unit, you have a causal quantity of interest. But the problem is that the red ones are not observed. For this quantity, we somehow need to either eliminate or replace them with observed outcomes, okay? We're not interested in individual effects because they're not identified, but we can take expectation over them. So first of all, I want to say one more thing about this interaction effect at the individual level. The interaction effect can also be interpreted as causal moderation, right? The interaction effect is causal moderation of G on Z. It is also causal moderation of Z on G, right? So these two are symmetric, right? When we first set out to write this paper, we didn't realize they're the same, but when you write down potential outcome, they're the same, right? So in other words, in our running example, you can say this is the causal effect of social capital on the impact of famine on mortality. You can also say that this is the causal moderation effect of famine on the impact of social capital on mortality. Although the second way, people use it less often because they don't think the event is manipulable, I think. But mathematically, if you're making that causal argument, they are symmetric. Okay, next we take expectation, right? Then hopefully they are identified. A key estimand is this causal interaction effect, or in some of the literature, people call it causal moderation effect. This is to say, in the example, how social capital reduced, here it's an action, so it's a causal interpretation, has a causal interpretation, reduce the mortality increase caused by the famine, right? So you have two causes here. One is the cause of the famine, one is the impact of the famine, the other is the impact of social capital on the impact of the famine, causal interaction. Another is associative on two causal effects, right? This is to say, okay, famine has a causal effect on places with high social capital. Famine also has this causal effect on the in places with low social capital. What are the differences? What is the difference between these two causal effects? All right, that's what we call causal moderation. Causal moderation interpreted as just descriptively. So one place experienced smaller or bigger mortality increase caused by the famine. Now here, if we are describing causal interpretation, actually we are comparing two different conditional effects. One is 1 minus 1 0, or the other is 0 1 minus 0 0. These two actually are not the same effect if you augment potential outcome with two indices, right? This is something, that's why I said earlier that it's not incorrect to say, so we are using DID to estimate treatment heterogeneity. It's not wrong, but to be more precise, we're actually estimating the difference between two different average conditional effects. Okay, so the question is, how do we identify either of this, either effect modification, which requires weaker assumption, or causal interaction or causal moderation, which requires stronger assumption. But people are more interested in such causal quantities. Identification. So here's a roadmap. As I said, I will not use mathematics. I will try to be as conceptual and graphical as possible. We have this statistical estimand, which is the probability limit of the DID estimator. And then we have four estimand. Some of them are causal, some of them are associative. The first one is an associative estimand or descriptive estimand describing effect heterogeneity, which is tau effect modification. And as I will show in 2 slides, that with no anticipation and parallel trend assumption, the DID estimator, these are the canonical DID assumptions. In this FDID setting, factorial DID setting, tau DID can identify effect modification as I defined earlier. However, if you want to, these three are causal, this is not causal. If you want to identify causal interaction, which is causal moderation, or a more conventional ATT in the canonical DID setting, or a conditional effect of G, so what is the social capital impact when the counties are exposed to famine, you actually require more assumptions. These assumptions are not unique, but we come up with sufficient assumptions that are we believe most interpretable. Okay, so first we want to establish the tau DID, which is statistical estimand, and the canonical DID assumption on the spatial parallel trends can lead to effect modification, right? Here we have, again, 2 groups, 2 periods. So I already wrote down what we can estimate, right? These quantities can be estimated under regular, normal regularity conditions. When law of large number works, you can estimate these quantities. As you can see, we can estimate Y11, Y11 before and after. we can also estimate y01, y01 before and after, because in the data, z equals to 1 for every county. So z, big Z, corresponds to the small z in the potential outcomes. So we can observe, right? We can observe or consistently estimate these quantities, these 4 quantities. And tau DID mechanically is shifting this line upward and connects to the starting point with the starting point for G equals to 1 group, right? Or you can do the reversely for the other group. All right, the question here is, under no anticipation parallel trend assumption, what does this statistical estimand mean? Here, there's no hat, right? Because we're talking about probability limit. Okay, so first we apply the no anticipation assumption. No anticipation assumption says that in the pre-period, no matter what happens in the second period, no matter whether you're exposed in the second period, y11 and y10 are the same, right? We can replace y11 with y10, and replace y01 with y00. This is important because it will allow us to apply the parallel trend assumption later. So we now already swapped 11 with 10 and 01 with 00. So next we applied the canonical parallel trend assumption, adapt to this framework. So no parallel trend assumption is defined for the potential outcomes when small z equal to 0. The parallel trend assumption is to say when the units are actually not exposed to the event, and the change over time on this potential outcome for G equals to 1 and G equals 0, they are parallel, okay? Again, but the tricky part here is that we don't know where these 2 red dots exactly are because we observe neither of them, right? This is different from canonical DID. Canonical DID, these 2 are the same. But for factorial DID, we don't know. It can be over here, but it requires these 2 lines. The 2 red lines are parallel, but we don't know the vertical position in the second period. Okay. Okay. Now with that, with no anticipation of parallel trends, it forces these 2 deltas to be the same, just mechanically, and because of that, the tau DID now can be interpreted as the difference between these 2 quantity and the difference between the differences between these 2 quantity and difference between these 2 quantities. All right. So what are they? If you look carefully, these are the average conditional effect for G equals to 1. This is average conditional effect conditional on G equals 0. This exactly is our definition of effect modification. So when these 2 assumptions are satisfied, tau DID identifies tau EM, which is effect modification. How the impact of famine differs across 2 groups with high social capital and with low social capital. Okay, but this is not saying anything about G's causal impact on the effect of famine. Okay, first we establish this this link. Next, if we want to say something causal, we need additional assumptions. So first, let's actually connect to the canonical DID, like a tau DID. If we want to say we're actually identifying the effect of the famine only in one group, not the other group, what assumption do we need? We actually need the so-called, we call it an exclusion restriction. It's very simple. It's when we figure this out, it's extremely straightforward. In order for factorial DID to return back to canonical DID, we have to impose exclusion restriction that the impact of famine on mortality for one of the 2 groups is 0, right? So here, let's say the impact on G equals to 0, equals 0. So then this second part goes away, right? So we are comparing 2 causal effects. But if one of the conditional effects equals 0 by assumption, then the remaining will be like analog of ATT, right? So if this red part goes away, if this delta shrinks to 0, then tau DID basically comes back to the average effect of famine on groups G equals to 1, right? So this is the exclusion restriction. This is stronger version, although we only need expectation of the two potential outcomes equal to 0. Okay, so under non-anticipation parallel trend exclusion restriction, tau DID goes back to tau ATT. So now we can frame canonical DID as a special case as factorial DID. This is not surprising at all, right? If you think about it. This is to say, although one group is exposed to the event, but the event has no impact, right? So just think about the canonical Karl-Kruger minimum wage example. New Jersey, there's a minimum wage increase, but Pennsylvania, conceptually, we can also think of Pennsylvania being exposed to minimum wage increase in New Jersey. You can argue there's a labor market equilibrium, and there's maybe spillover. So you conceptually, Pennsylvania is also exposed. But if you are willing to impose additional assumption that although Pennsylvania restaurants are exposed to minimum wage increase in New Jersey, but there's no impact, or on average, there's no impact, then the DID estimator will give you back the ATT if these assumptions are satisfied, no anticipation parallel trends, the ATT of minimum wage increase on New Jersey restaurants. So that's the simple logic. But once we have the exclusion restriction, the tau EM, although this is an associative estimand, become a causal estimand. That's pretty awesome, right? So even without the original one is associative, but this one now becomes causal. Okay, so now the question, a more difficult question, this definitely not applying to our example because obviously both type of places are exposed and affected by the famine. But you want to say we're identifying causal moderation, what assumption do we need? So first of all, just to pin down the interpretation, why we need additional assumption. I'm sure listeners or audience here must have realized because G is not randomized, because the baseline factor social capital can be correlated with a million different things, right? Can correlate with human capital, with culture, with crop suitability. Although in our paper we try to rule them out by controlling the interaction term between these additional baseline confounder with the time dummies, but you can never rule everything out, just like in unconfounded design, right? It's a classic omitted variable problem. So here, imagine there's an observable U that determines how units respond to the event. It's not G, it's just U. But happen to be the case that G and U are correlated. So if G doesn't matter, if U is small, then the impact of the event on outcome is smaller. If U is larger, then larger. However, because G and U are correlated, so you observe a bigger impact for this group simply because U is bigger, not because G is 1. But since you don't observe U, you attribute this bigger difference as the causal impact of G, right? That's just a classic unconfounded or confounding assumption on the variable type of argument in a panel setting. All right, so that's why we can only describe using DID estimator the effect modification. We cannot interpret as causal because G cross-sectionally is potentially correlated with a lot of different things. So that's the reason. Okay, so if you stare at the mass, so the effect modification is the difference between two average conditional effects, and causal moderation or causal interaction is also a difference between two average conditional effects. However, it is not conditional on G, right? It's aggregate over everybody in the sample or in the population if you take an expectation, right? It's not conditional on G, and the conditional on G introduces potential biases, right? This is causal because we are comparing the 4 potential outcomes for the same group of units, which is everybody. But these are not causal because we conditional on G equals 1, G equals 0. So how to make them equal, right? There are a million different ways to make them equal because you can always minus and plus things. But I think, and we think, and also the authors in this paper seem to implicitly assume is that we need some kind of orthogonality between G and the first difference of all pairs of potential outcomes. Okay, we can find weaker assumption than this. We can make a mean independent instead of independent. We can also don't need all the groups, but this is what is conceptually simpler to interpret, right? Okay, so this is what it is. This is orthogonality between G and the first difference potential outcomes. So basically, the panel structure, especially when you are using DID estimator, allows you to relax the assumption of G is orthogonal to everything to G is orthogonal to the first difference version of the potential outcomes. Although we are working with 4 different types of potential outcomes. The G and Z can be Z0, 0, 0, 0, 1, 1, 0, 1, 1. Okay, but it's weaker than the conventional quasi-random assignment or unconfounded if you conditional additional covariates. Okay, so now the additional thing, so we've explained what it takes to arrive at causal interaction or causal moderation. The last thing is, in some papers, people actually use the DID estimator to estimate not the causal moderation, but the conditional average effect. So they're interested in, for example, in the religiosity paper, they're interested in whether religion actually, maybe, right, that's my reading, it's a little bit vague. Maybe the authors are interested whether religion has a impact on growth, economic growth, when the Industrial Revolution has already happened. They don't care about the difference between before and after, but then you need additional assumption that Y10, Y11, when in the post period, when they're not, the units are not exposed to the event, there's actually no impact. Basically collapse these 2 sets into 1 set, then the causal interaction also becomes the conditional average effect, right? Eliminate the second part. Okay, so that's the, sorry, not the second, eliminate these 2 differences. Now it only becomes Y11 minus Y10. It is also causal because it's a causal impact of G. Conditional on the units are being exposed to the event. Okay, the last 2 things, a sufficient assumption needed for EM to become C or causal moderation or causal interaction is this quasi orthogonality between G and the first difference potential outcomes for all pairs, right? And then if you are willing to add additional assumption that when Z equals 0, G has no impact, then you arrive at the average conditional effect. I know it's a lot of effects. In the end of the talk, I will provide you what this means in our learning example. So it's not that abstract. Okay. All right. So to summarize, canonical DID, you have one group that are not exposed in the second period to the event. So non-anticipation parallel trends can identify ATT. However, we can also reframe it under universal exposure. So everybody is exposed, but if you're willing to add additional assumption that one group is also exposed, not affected by the event, tau DID can still give you tau ATT. In the factorial design, when you don't have the causal interpretation, then it depends on whether you're willing to add additional assumptions. If you're not, then you're identifying causal effect modification, which is associative. If you're willing to add additional, potentially very strong assumption on orthogonality, of course, you need to worry about confounding, right? Because G is potentially correlated with a lot of cross-sectional covariates. So you can identify causal interaction or causal moderation. If you, on top of that, you're willing to add exclusion restriction on G, then you identify the average conditional effect of G conditional on Z equals to 1. Okay, for time's sake, I'll skip that part. And we very happily realize actually our finding is connected to the LOD paradox. It is a paradox only because that when people are estimating are using different estimation strategies. They actually impose different assumptions on the potential outcomes, on non-treated potential outcome or non-exposed potential outcomes. So here in factorial design, we make it very clear what are the potential outcomes, what assumption you need. So it's not a paradox. Okay, so extension. These are all fine, but in real world application, real research applications, we actually have very commonly additional covariates, and also we have multiple periods, and we have multiple values of G or continuous G. Here again, I just very briefly talk about what we can do and the lessons we learned from extending our framework to this slightly more complex settings. So first of all, with additional covariates, if we are willing to relax assumption of like parallel trends to compare conditional parallel trend to the ignorability, the orthogonality assumption to conditional orthogonality, then arguably these assumptions are more likely to hold. When you have those, you need to like use more complex estimation strategy. So this specification is very common, all right, in the applied papers. In our paper, we also use this so-called horse race. It's a horse race because we put interaction between G and post time dummy, but we also put a set of covariates, like I said, human capital, crop, culture, population, so on and so forth, interacted with the post dummy, right? And why do people do that? Why do research do that? Because they don't believe that unconditional orthogonality. They believe when you condition on these things, when you rule out these obvious confounders, maybe G is orthogonal to first difference potential outcome. Although they don't say that in the paper, it's a bit vague, but I think intuitively they understand they need to rule out additional confounders of G and the first difference potential outcomes. So what we think is that this is the reason, right? They believe this conditional version is more plausible than the unconditional version, although they're not implying or derived by each other. But we can believe that after stratification, this is more likely to hold. But with the preparation that we already have, we realize, okay, so because of that, because we're actually just modeling the first difference potential outcomes, we should allow a little bit more flexibility. So we should add a triple interaction between G, X, and post to allow the model of delta Y and X and time to be flexible across groups, right? So that's the reason we want to add a additional term. This is analogous to the Lin estimator in the experimental literature. When you want to control for covariates, you want to control for the interaction term between treatment and covariates. Also, you want to include the covariates linearly, but you also want to include interaction between treatment and covariates, right? That's the link. But here we need a triple because we already have a difference because of time. And this also tells us that you can actually transform data into cross-sectional and then redefine the problem by replacing Y with delta Y. Then you can apply all the estimators developed under unconfoundedness or selection observables to apply to this FDID setting. We actually developed a package that allows you to apply balancing, matching, IPW, AIPW, even double machine learning to this transformed Y data. Okay, that's so we can actually extend this to the model machine learning or the more flexible models, estimators. And second extension is when you have multiple peers, what do you do? It's the same. You can return back to 2x2 DID estimator just by rotating the target period. But there are two lessons. One lesson is that you want to do pre-test, like a pre-trend test, as we often do using event study specification. But this specification only allows us to gauge no anticipation and parallel trend assumption, but not this independence assumption, right? We cannot imply or gain confidence of this independence assumption by just looking at whether there is pre-trend. Even there's no pre-trend, we don't have additional evidence on this orthogonality assumption, okay? Second lesson is that oftentimes you will have a carryover, so you don't want to just dummy out this event time as most papers do. You also actually want to have a post-event period to allow carryover. This is like a temporal interference because event. Okay, that's the second lesson. Another thing we include in the paper we didn't have time to cover is the continuous G, but you can either, the two ways, you can either discretize G or or to make it, to bing G into several groups, as we will do here, or you can add additional functional form assumptions, like 2f(x)(5) is a strong functional form assumption, right? So these are the two options. Okay, return back to our example of clans and famine, clans and calamity, which is famine. As you can see, it's a very deadly event because of disastrous policy of Greeley-Ford. The famine is 58 to 61, although in China people call it 3 years of natural disaster, 3 years of famine from 1959, but many historians believe the deaths had already happened in the winter of 1958, so we include them in the event. All right, the social capital is a measure of number per capita level genealogy measured before the founding of PRC. Again, you've seen this. So we can condition on a bunch of covariates that are potentially correlated with G and the first difference potential outcomes. These are applying to different estimators. This is canonical to f(x)(5) without additional interaction terms, three-way interaction. This is with interaction. As you can see, if you make the functional form more flexible between the two groups, you actually have a sizable difference, right? And these confidence intervals are obtained by non-parametric bootstrap at the level of I, at the level of county. And then, sorry, these are adding covariate, these are adding three-way interaction. These are using flexible outcome model, generalized random forest. This is the IPW. Also, the propensity score is estimated with GRF, this AIPW. Both the outcome and propensity score are estimated with GRF. You see the confidence interval shrinks a little bit, but comparable to the three-way interaction. Okay. Dynamic specification, this is without control. Without control is basically different diff. So with control, you have larger effect, larger difference. Be very careful about interpretation. So with additional three-way interaction, you have an even larger and more precisely estimated differences. Okay, this is AIPW, fairly similar. All right, so now what about the multi-value G? G is, in our data, G is a bunching at 0 because a lot of counties have no genealogy books remain after PRC was founded. So we basically discretize into 3 bins and estimate them between group 0, group 1, which is a low level social capital, and group 0 and group 2 compared with high level social capital. You can see that the difference mainly driven by places with a lot more genealogy books. Okay. All right, so to summarize our interpretation is really important. This is also what I'm teaching my student about. You are using this estimator. First, you need to lay down what you're estimating, and then if these assumptions are correct, you need to specify these assumptions, and then what can we say about these estimates. We have 4 estimands, and we have different names for them. So effect modification means how the average effect of the exposure to famine mortality differ, right, between counties with high and low level of social capital. Only require no anticipation parallel trends. ATT is to say what's the average effect on famine in counties with high social capital. So assuming, or low social capital, assuming the other group has the famine has no impact, right? This is obviously very strong and not plausible in our example. Causal interaction, causal moderation is to say, how does social capital causes or lead to or mitigate the impact of exposure to famine, right? But we need additional orthogonality assumption, maybe a conditional version. If we're interested in the average conditional effect, this is to say, what's the average impact of social capital mortality during famine years when everybody exposed? But you need to assume that in the famine years, when these colonies are artificial or like counterfactually not exposed to famine, and this social capital would not matter, right? This additional exclusion you need to assume. So in our paper, in our running example, in my paper, I think EM is obviously most plausible. If you want to stretch a little bit to assume this to be true, you can say causal moderation. These other two exclusion restrictions are definitely not plausible in our example. But in other example, it may be plausible. Practical recommendations. First, you still need to assess pre-trend. This gives you more confidence in the non-anticipation parallel trend assumption, which are absolutely needed, even for effective modification. All these four estimand that are interpretable, they need no anticipation parallel trend assumption. And second, if your goal is to say something causal about G, especially causal moderation, you need additional assumption, which is very strong, which is not directly testable. You probably also need to do sensitivity analysis to shed light on how plausible additional confounder can explain away this correlation, right? In terms of estimation, if you use two fixed effects, I forgot to mention, when you include additional interaction terms, you also need to demean the covariance in the sample. This is the same reason in the link estimator, you need to demean the covariance in the experimental data. Then it makes the model more flexible. Also, you should not assume no carryover. There will be, in many cases, there will be carryover. So that's what you can adopt in terms of, in addition to interpretation, in terms of estimation, you want to engage in assumption, additional things you can do. All right, I'll stop here and answer a question. Thank you very much.
Okay, thank you very much, Yi-Qing, for this great talk to bring two strands of research design, the factorial design, the DID design, and to give a very great summarization regarding the connections and also difference and also the improvement of the research design and the method. Now the floor is open to accept questions. There are two ways you can raise your question. One is to just input your questions in the chat box so that I can read for you, or you can just read by yourself. Otherwise, you can also just input briefly the word question to indicate that you have a question, and then I can call you when it is your turn. So now the floor is open. Okay. So the first question I think comes from Professor Eric Hekela from UCL. So Eric, please.
Thank you. Professor Xu, I think that was a really wonderful presentation. I'm reminded one of my heroes in academia, in the circles close to me, is Professor Arthur Geddes, who passed away a few years ago. And one of the reasons I think so highly of Professor Geddes is that when he spoke, I felt smart. And when he stopped speaking, I would be me again, So he had a way of sort of elevating my sense of comprehension. And I find that same quality in your presentation. You distill the elements so nicely that it makes me feel as though I understand, even though I really don't. But I just am feeling sort of a sense of clarity. So first of all, and that's to me quite rare. Even the way you prepared your slides, with the slide along the bottom, letting us know where we were and which slide it was and how the thing was progressing, and your graphics, there's a clarity to it that I think comes with just, it feels like you have a knack for dispelling anything that's unnecessary and leaving us with just the essential elements. And so much of not understanding things is having clutter in our minds. And you do such a nice job of removing the clutter and leaving, allowing us to focus on these other elements. So, with that in mind, I'll maybe just try to say what I think I learned and leave it to you to correct me or to expand, because I come in knowing almost nothing about this. So, as you define it, it seems like the canonical version of DID, based on your presentation, is that the key is the group, and the group is exposed, right? That's the key, that there's a perfect correspondence between those who are in the group and those who are exposed. And of course, that might not be the case, right? And so your factorial approach is allows for that not to be the case, and in different dimensions. And there are different ways that that might not hold, right? Some of those who are in the group might not be exposed. Some of those who are not in the group might be exposed, etc. And your different estimators correspond to those sort of the relaxation of that of that kind of hard constraint in the canonical model. And so your factorial model clearly is more powerful because it encompasses the canonical model as a special and indeed highly constrained case of the factorial model, and indeed your parameter estimates that you're providing, all these different taus, are showing kind of the shadow price, in effect, the shadow of that constraint, of the constraint embedded in the canonical assumptions, and you're doing it sort of around the edges of each of those. So I guess my first question is, how wrong am I? And if you can correct that. And the second question, I guess, is just in terms of the actual famine. What is your answer? Like, if one does it, if one does the estimation according to the canonical version, what is the effect of social capital on this using the canonical version? I thought you might be ending with sort of, well, that might have been a 20% surplus, but in fact that 20% surplus, 13% of that was due to this effect and 5% was due to that effect, and kind of a decomposition of what would have all been lumped into one estimator in the canonical version. I thought that your final slide might have been that. So I'll leave it at that and bow out.
Thank you, Professor Hakila. I don't know whether I'm butchering your name. Please call me I Ching, and thank you for the compliment. Coming from you is very important to me. I think you're exactly right that we are talking about, we try to clarifying our research design with different target estimates. But here I may have confused some of you, which is that you can, in the later part of the talk, we did talk about additional estimators, but in the majority of the talk, the first 40 minutes, we're talking about the same estimator. So we're not using different estimator, we're using the same DID estimator. So on that part, there's no different estimate. There's only one estimate, which is coming from the DID or two-way fixed effects. But in the first 40 minutes, what I wanted to say is that depending on how strong or what kind of a group of assumptions you're willing to impose, you will have different interpretation of this DID estimator. And some of them are associative, some of them are causal. I want to remind people with this paper that if you want to say something causal about G, you need a stronger assumption than you normally believe. I think that's the main message of the talk. Although you may also ask, why should we commit to the DID estimator? This seems to be a very dumb estimator. But part of the reason is persistence of usage of this estimate in the literature, and I want to clarify what are we actually doing. Many researchers, and with this additional clarification on the potential outcomes, I think we can come up with better estimator, as we alluded to at the end of the talk. So for the famine, it's also my fault not to give a magnitude of how large is the impact. So if we believe the additional orthogonality assumption is true, that conditional on additional covariates, there's actually a orthogonality between social capital and the first difference potential outcome. It's about like 20 million. So the social capital, if we assume all counties have no social capital, no clans, so we measure social capital using the genealogy book, which means the vehicle of social capital is clans, where there are a lot of unofficial lending and borrowing and supporting and hiding a grain during the famine. It's about 2 million people, 2 million lives were saved because of the presence of the clan. That's the magnitude. It's about like a one. So the overall is like increase is about 2.5 percentage in terms of mortality rate. It reduced mortality rate by about 1%, something like that.
Can I just ask? I'm very sorry to interrupt, but can I just ask on that point, when you say sort of 2 million additional lives saved, right? But were those at the expense of other lives that were lost? Was it just a question of the social capital intensive clans being able to offload deaths to others?
That we don't know. That conditional other covariates may be also correlated with reduction of deaths. One particular confounding we find very highly predictive is human capital, is 进士, actually, whether there were 进士, historical exam winner, explains a lot. So there's a cultural element in that. So conditional on that, there's additional 2 million lives saved when you can imagine we can shift the level of social capital from low to high. So that's approximately and we cannot do much decomposition, but as I said, it depends on what assumptions you can decompose in a way that, okay, so associatively, descriptively, these are the differences. But when you condition on additional covariates, whether the association shrinks or becomes bigger, we can do some of that, but we cannot decompose between effect modification, causal moderation, because they are two completely different estimands. Thank you so much for your comments. It's
Well, thank you.
It helps me to think about how to present results better.
Okay, so our next question is from the chat box, which is raised by Peng Huang. Peng, do you want to raise your question by yourself, or do you want me to help you read the question?
Oh, sure, I can read out my question. So first of all, thanks, Dr. Shi, for this very fascinating talk. My question is about your suggestions or your recommendations of how we deal with the situation when our observation have autocorrelation structure. And I think in your empirical example, it might be a common scenario where our analytical unit are geographical areas. And we know that typically in a lot of spatial analysis, we recognize that our observation may have some autocorrelation structure, either because of autoregression or because of spatial lag or because spatial dependency. So in other words, whether either the residuals are correlated to each other or the outcome themselves are correlated to each other. So I'm curious about what's your take of in your factorial DID design, how we should think about this potential autocorrelation structure and how we can model this and how that is going to influence our identification. Thank you.
This is a great question. Thank you, Peng, but I don't have good answers to because we are to some extent, we're committed to the DID estimator, which it's a very primitive estimator. But in terms of, I can just answer from a very practical point of view. If you're worried about spatial correlation, then it's yeah, if you know how to model the spatial correlation, you can improve precision. But if you don't have much knowledge about how the spatial correlation works, then it's more about the inference, whether the inference is legit, right? So you can imagine cluster at a higher level or non-parametric bootstrap at a higher level. That's fine. But if you worry about, so the inference will still be correct, although you lose some, you leave some information on the table, not getting a more precise estimate. If you worry about autocorrelation, if you more longer time series, as we kind of do, like longer time series, if you just do 2 by 2 DID, you're also wasting a lot of information. But then we really are moving away from the DID as the structure, right? So we're in the DID, we are committed to this very simple structure. And then another question is, if you're moving, so I think there are a lot of gain. There will be a lot of gain because knowing about the pre-event mortality rate will, especially for variables like mortality, is pretty stable, pretty predictable without the event, right? So you can imagine you can impute non-treated potential outcome, non-exposed potential outcome much better. But here the tricky part is that we also not only need to come up with the given G, what's the non-trivial potential outcome when Z equals 0, but also the other group, when G is of opposite value, you also need to impute that potential outcome. So with DID, you have this parallel trend assumption. With a more complex and more powerful time series model, you also need to make some structural assumptions to link the two groups together, right? To link the 8 potential outcomes together. That's certainly doable. I think you can, I can imagine you can make very sensible assumptions on this and gain more precision. But we haven't done that mainly because we want to first have a conceptual clarity, but that's like something very worth to do.
Okay, thank you. So the next question will be from Zheng Zhang. Zheng, could you please just raise your question by yourself, and then following by the question from Professor Jamie Lee. So Zheng,
Yes. So
okay.
I first want to echo with what Eric and Peng said about your presentation. I think it's conceptually clear. It also gives us leverage over modeling the reality. I think this is what all the empirical work should pursue when it comes to modeling. So I actually have many questions, but I will just start with 2 because I just don't want to take over the Q&A session. So when I was listening to the first few slides, I was thinking about the question. So when we assume the estimator modeled from canonical DID, but it's actually a factorial DID setting, which means the treatment actually applies to both treated group and untreated group. So the estimator we got is actually has underestimated the true causal effect because he has already subtracted the effect of untreated group because it has been affected. I was just thinking about what's the sort of the consequence of not having a properly defined factorial DID when it is the case in reality. And the second question is about the first extension you presented. It's about when, for example, the social capital has other confounders, and so we will interact the estimator of the DID and other confounders. I was just wondering what quantity should we take, or what estimator should we take in that setting as the causal effect? So these are the 2 questions I have.
Okay, so for the first one, so in this setting, so we have, can you see the slides? So we have this so-called dynamic specification, estimates from the dynamic specification. I think in our review of the empirical papers using such a setting and such a research design, I think nobody interpret this as a treatment effect on one group. They all know it's the difference in treatment effect between multiple groups, between two groups at least. So I don't think there's a confusion about their estimating. They forgot to there's a subtraction of the effect on the other group. Because if you are careful about the plotting the raw data, looking at the raw data, you will not take the difference between these two as the effect for one group, because obviously you're subtracting the effect if it is effect from the other group. So I don't think there's people are conscious about what is different. People know it's different from DID, so that we need to give credit to them, but they don't know exactly what they're estimating in causal language, in very precise causal language. That's what I think is a little bit contribution of this paper. In terms of when you have covariates, we're actually targeting the same causal moderation as estimand. We're just, because we're allowed to condition on covariates, maybe the orthogonality assumption. In the paper, we call it factorial parallel trends, because it's parallel trends on each of the four potential outcomes is more likely to valid. This is like to say, just imagine the confounded setting or selection observable setting. If you don't condition on additional covariates, it's hard to believe this treatment is orthogonal to a potential outcome. But now you are able to control for this variable that have a lot to do with the selection. Maybe you're more comfortable with these estimates with covariates included are giving you a causal estimates. So that's the difference. In terms of the estimation strategy, as I said, I think a simple improvement is just a two-way fixed effect with a three-way interaction. That would be our advice, like just estimating this equation. Although you are still imposing some linearity assumption between covariates and the delta y, but that's already better than not allowing this relationship to be different across groups. But you can, as I said, you can use more advanced non-parametric estimators if you have more data.
Just a quick follow-up on the slide. So when we have confounders here, do we still interpret beta t as the causal effect, or it needs to be beta t plus?
No, we interpret tau as the causal effect of G on the impact of the event. If we believe this assumption.
Yeah.
Okay, thank you. So our next question comes from Professor Jamin Lee, our colleague in the Department of Sociology. And also for the sake of time, this will be the last question we will receive for today's talk.
Okay, thank you for that opportunity, Ling. Yeah, I just want to thank you for the opportunity to learn a lot about this DID design method. I personally use experiments and also use causal inference, but I'm really quite naive in terms of this quasi-experiment method. So thank you for that. So in the end of this talk, so there are lots of thoughts lingering around my head, how to apply this factorial DID in empirical sociological research. As the key here is to find the setting that satisfies all these required assumptions, like no anticipation and parallel assumptions. So my question is very naive. At the same time, it's very practical. So do you have any research going on your side or others benefiting from this design presented in this paper? So that would help like the audience, especially students here, they can think about and brainstorm how to apply this setting. Thank you.
Great. This is a great question. I'll actually return back. I will just return back to, to the four example that not my own, but by other people. I think that's potentially helpful. It's all right. These four examples. Okay. So I think so the reason why this kind of a research design is popular across social sciences, also sociology, we have some examples too. We found some examples, is because especially for historical analysis, to collect panel data on the treatment is very expensive. So for this kind of design, you only need panel data for the outcome, like the mortality rate or economic growth. That's all you need. And then the additional variables are the cross-sectional, right? G is cross-sectional. And then you have an event. So all these papers are like that. So you don't have to track how the treatment or the G variable change over time, which is very difficult to do with historical data. So like this example, it's a very easy to understand example, which is, okay, you have this presence of clergy or Catholic clergy in French departments, and how their presence will moderate the impact of industrial revolution, right? So to ask a researcher to collect how the density of Catholicism evolves over time, like a few hundred years ago, it's very difficult to do. That's why this kind of research design is so widespread.
So I've seen the last table you prepare, right? So in all the cells, the 2x2, you mentioned all in all the scenario, whether you interpret it as a causal estimand or non-causal, or providing a non-causal explanation, parallel trend is always a demand. It's always required. So
Yes.
what if we do not have that parallel trend? Because I've seen many studies, they so-called difference in difference or regression discontinuity, but actually they do not have those parallel trend, but they still want to use this.
You cannot even interpret the DID estimate as effect modification.
Okay, but they can still provide some substantive interpretation for those findings, right?
No, we don't know.
You do not even think of that?
No, we think of it, but it's not. You're not identifying anything. You have a DID estimator. You get a number. That number does not correspond to anything interpretable.
Okay. Yeah.
So I think here we start to realize more and more to distinguish statistical estimand and causal estimand. Statistical estimand is something that you can estimate consistently from data, but that's a set of moments, right? The subtract and then addition of moments, but that moment may not be interpretable.
Yeah, but I do have observed many studies.
Yeah, many studies are not identified, right? That's fine. A lot of studies are not identified.
But they're still published. So this will surprise me a lot often when I come across those papers. So yeah, but I think I get your perspective regarding this type of findings. And that's also my own understanding. If you do not have the parallel trend, to some extent, it is not highly not just not highly. I don't think they are quite comparable. Not quite a good estimate for the question.
By the way, the parallel trend assumption is not testable. So it involves counterfactual. So we do not know whether it's satisfied or not. But you can.
But at least we can use some descriptive patterns, right? So even based on those descriptive patterns, if you do not have the parallel trend, to some extent, then it's like the treatment group versus the control group. If they do not have the parallel trend before the event, that's the situation.
Yes. But so as I should have been clearer. So looking at the pre-trend, we can gain.
Give you some sense, yeah.
We can gain confidence in the parallel trend assumption, but we don't know exactly whether it's satisfied because the parallel trend assumption involves counterfactual, happens in the event period. So we don't observe that. But if they're always like parallel to each other, we are more likely to believe
more confident.
They will stay parallel when the event didn't happen.
Okay, it's well on time. So 11 o'clock. Thank you, Professor Xu, for this great talk, and thank you for all the participants for your great questions. So see you on our next CSSL webinar. Yeah, see you everyone. Bye.
Thank you so much for having me. Thank you for the great questions and comments.